All right, so our first problem, we're going to be finding the volume with a solid with, it says base, but it looks like babe, shown if every cross-section is parallel to the x-axis is a triangle with height equal to twice the base. So first let's go ahead and imagine that triangle. Where is it at? So the triangle here is going to be, we'll just pick somewhere in the middle. So that's going to be a triangle. And this is its thickness. So we're kind of looking down at this at an angle. Really, if we're looking right down on top of it, we would just see a slit. We'll just see a thickness bar. So this dt represents the thickness. Sorry, this green bar represents the thickness dt. Now what this triangle actually looks like to us, if we're looking at it down the y-axis from this direction, it would look like that triangle right there. And we said that we have a base here, and we said that the height is twice the base. All right, so that's our relation. And we want to use the base as a relation because that base is what's embedded in the graph. Height is in the z direction. You can't see it. You can't see it when you're looking down the y-axis. So we have to use our base as a relationship because that is what's going to be the independent. Because that's what your height is dependent upon your base, which is dependent upon the graph. So we know that volume, a dV must always equal your area times your thickness. So we need to get each individual area, which is going to be an area of a triangle, which you know is height times base over 2. We know that each base, right now we can go ahead and call this x. That length is technically x. But one thing we need to look at it as, if we have an element thickness that's horizontal in our strip, then that means that we need to use dy's because that's what this represents. This represents a dy. So even though this length from here is x, we need to do it as x2 minus x1. So that is what's going to be our base. So for us, x2 minus x1 is really just going to be x2, meaning this equation here. So it's going to equal the square root of y. So that's going to be our base. So we know that our height is twice the base, so we have 2 times our base, square root of y. We have our base, which is the square root of y, divided by all by 2. 2's cancel. Times our thickness, which we said it has to be dy. This will equal y dy. And if you want volume, we have to integrate everything. And we have to integrate it from 1 to 4. So this is y equals 1. This is 4. All right. And the reason why we have to do dy, just to reiterate, it's because this is our element thickness. It's parallel to the x-axis, meaning every strip is going to be based off of a dy. Each element volume is based off of dy. So now we can integrate this. So it's going to be 1/2 y squared from 1 to 4. And that'll be 1/2 16 minus 1. So it equals 15 over 2. All right. So now this next one we have repeat, except every cross section is parallel to the x-axis, is a quarter circle. So instead, each of these thicknesses, I'm just going to draw out the thickness here. Each of these strips is going to have this shape. A little box here, then we'll draw that again. That's a little better. So we have a quarter circle. So it's going to be the same thing we did before, where we said d of volume is going to equal the integral of a dt. But instead of height times base over 2, we're really going to have the area of a quarter circle, which is just going to be the area of a circle divided by 4. So it's going to be pi over 4 r squared dt. All right, so this is going to be our r. All right, so if this is our r, we can do the same relation that we did before, because we said r is equal to x, which is equal to the square root of y, because we still need to use dy's. So it means we can integrate this as pi over 4 y dy from 1 to 4. Literally the exact same thing. The only difference is we're going to have a pi over 4 being multiplied by this. So 16 minus 1 is 15 pi over 8. So again, all this is about getting your ADT, knowing what your strip is. If it's horizontal, you have to do dy. If it's vertical, you have to do dx. And your area is going to be dependent upon wherever that cross-sectional is. So in this case, they give us a triangle with a relation to the base. Remember, this has to be your base to the height, so you're able to get the area of the triangle. Same deal here. They gave you a circle, which you know that this r represents how you can get the area for an entire circle. They say quarter circle, so you just divide by 4. If it's a semicircle, so be careful. If it's a semicircle, they may ask you that. The length here is no longer r, it will be a diameter or 2r. And then you have to then you have to do it by that instead. So be careful about what shape you're looking at and what you're going to be doing. Just try to think about how you find the area of whatever that cross section is and relate it to your element of area, so either a vertical strip or a horizontal strip, and how you can use the equations that it relates to get that relation. All right, so this next one we have find the surface area generated if the arc y equals 4 minus x squared from 0 to 2 is revolved about the y-axis. Show r on the graph. All right, so on this one we need to really we need to go ahead and figure out our surface area equation. So I say dSA, so this is for one individual surface area, it's going to be your circumference, so 2 pi r, times your length, because this is what a shell is. Not shell. This is how you get the surface area for a cylinder. So it'd be 2 pi r circumference times ds, the length. How far does that circumference go? So if it was perfect, you can just say ds is equal to 1 for a cylinder, because it wouldn't change as you go about this axis. It would just, this whole thing would just be whatever it is. This would be say 10, and we have r equal to 1, and we're able to figure out that surface area really easy. It'd be 2 pi times 1 times your length ds, which is 10. But we don't have that. We have a varying length, or a curved length, which means we have a varying ds. So we need to find the surface area generated if the arc y equals 4 minus x squared from 0 to 2 is revolved about the y-axis. So again, y-axis. So wherever it's revolved about, that's going to be telling you what your r is. So because your radius should always be perpendicular to your axis of rotation. So that's our r. All right, so now we know that this has to be our thickness ds right here. So we need to be able to figure this out for any given position. So if this, and we can do this in terms of x or in terms of y. So if we try, I have to problem solve here. There's no really easy way to know which one to do. Normally I say try in terms of x and see if it works out, and if it doesn't, do it in terms of y. So they give you in terms of x, So go ahead and try in terms of x first. So that means that this ds, so it'll be 2 pi, our r, again, that'll be x, because it's going to be the distance from our y-axis or axis of rotation. And remember, your axis of rotation can be something that's not an axis, or not a y or x axis. So if the axis is over here, you need to account for that distance, wherever it is. If this is 1, then make sure that your radius is going to be 1 plus whatever this distance is. So in this case, radius r is going to be from the y-axis out, which is x. That's your distance. But again, if you have the axis over here, it would be x plus whatever it is for your relation for your radius. So in this case, r is x. And then we have ds, which is going to be 1 plus y prime squared. Y prime is equal to minus 2x. So it's going to be 1 plus 4x squared. And dx. So we're looking, we have to make sure that, is that going to be integratable? And it is. If you make this our u, we're going to get 1 plus 4x squared du equal to 8x dx. So we have that x dx to assist us with our u. So we know we can integrate this. All right, so now we can get it into the form of an integral. So we know that surface area is equal to integral, and we're doing it in terms of x. So we know that x is going to be going from 0 to 2 because we're going from y equals, we're going for x equals 0, which is at the axis, to whenever y equals 0. So if y equals 0, it's going to equal 4 minus x squared. So x squared is going to equal 4. X is going to equal plus or minus 2, and this is going to be the positive side of that 2. So we know it's going to have to be 2 here for x. So it's going to be 0 to 2 for x. Then we have 2 pi. I want to actually pull out that pi out front, because I'm going to have to, I know I'm going to have to substitute in for it in a second. Or not substitute, I'm going to have to multiply by a factor to help me integrate this. So x square root of 1 plus 4x squared dx. So now I can go ahead and multiply by whatever I need. So I need an 8x out here, so I need to multiply this by 4. Oh, sorry, I need to divide this by 4. And multiply the inside by 4, because again, this will be 8. So now I have my du, my u, I'll underline it twice. So I have a u to the 1/2, and now I can integrate that. So it will be pi over 4 times 1 plus 4x squared to 3/2. Make sure you divide by that 3/2. So 2/3 here from 0 to 2. So you would cancel this out to 2. So you have pi over 6. Go ahead and plug in for your value. So I'm going to plug in 2. I'll have 1 plus 4 times 4 to the 3/2 minus 1 to the 3/2. So this will equal pi over 16 times, this will be 16 plus 1, so 17 to the 3/2. So it would be 17 square root 17 minus 1. That is the final answer. Oh, and I forgot to mention, and I've been bad about it, but make sure when you go through all of these, you make sure that you do, you know it's a volume, so length cubed. This is a surface area, so length squared. All right. Sometimes they're okay with it, but it's always a good practice to get into. So next one says use disk. So it says use disk. We know that our dv is going to equal to pi r squared dt, where r is our distance from the axis of rotation out to our curve, dt is our thickness. So in this case it says use disk to solve for the volume generated if the region is revolved about x equal to 1. So in this case x equal to 1 is right here, which means that this is our r. So we need to figure out this relationship between r and x, because that's what we're kind of dealing with. Because if we're rotating about the x-axis, we know that this distance here from here to here is 1. The distance from here to the curve is x. So we need to create a relation there. So I know r plus x is going to always equal 1, which means r is always going to equal 1 minus x. See, I did that because this is the sum of what x and r equal to. This is a portion of x. This is the portion of r. And I know that they're going to add up. And I probably should have drawn r and x at the same height to show that relation. So r would be right here. This would be x. So that way you see that their lengths actually equal the overall 1. So I know that r has to equal 1 minus x. And that makes sense. If x equals 1, means it's all the way out to here. My radius here is 0, because again, it's going to be about the x-axis. All right, so now I need to figure out if I'm going to be doing this in terms of x or in terms of y. So your strip in this case is going to be for a disk is going to be we're going to go back to that little worksheet here, the review. So wherever you rotate is going to have some thickness to it, and you revolve it. So our thickness in this case, going back to that problem, the thickness in this case is going to have to be parallel with r. Or the thickness is going to be perpendicular, but the strip is going to be parallel with r, meaning that this is going to be a strip of area right here. So that's going to be a strip of area. That means we have to use dy. So your strip should always be perpendicular to your axis of rotation when dealing with discs or with washers. Remember that. Your strip should always be perpendicular to your axis of rotation for discs or washers. It's the opposite for shells, though. So we now know this is going to be r is going to equal 1 minus x squared, but we know that this has to be in terms of dy. So we need to get 1 minus x in terms of y. So we know that x is equal to y squared because we can get that relationship from this y here. So I can just square both sides and I get x. So I know that r is going to equal to 1 minus y squared. All right, so all I have to do is plug that in and I get pi times 1 minus y to the 4th now, or sorry, y squared dy. So now I can integrate this to get volume. This is going to end up just being basic power rule. So volume is going to equal the integral. We're going from 0 to 1. I'm going to pull the pi out front. We'll have 1 minus 2y squared plus y to the 4th dy. So it'd be pi times y minus 2/3 y cubed plus 1/5 y to the 5th from 0 to 1. This will equal pi times 1 minus 2/3 plus 1/5 get a common denominator for all of that. It'll be 15 over 15 minus 10 over 15 plus 3 over 15. So we'll get 15 minus 10, which is 5, plus 3, 8. 8 over 15 times pi. And again, this is a volume, so length cubed. All right, pretty I would say straightforward, but there's definitely a process to it that you can definitely figure out. All right, it says set up but do not evaluate. So this is where if you really understand what you're doing, you don't care about the number, you don't care about the algebra, you just care about how you set this up. But this is in terms of one integral and one variable. So it means that we can't have x and y's in here, and we can't have two splits off. So we make sure we do this optimally, meaning we only have one integral, and we can't have anything split up. All right, so we need to find the volume generated in the area shown if revolved about whatever axis they show. In this case, we need our line is x equals to 2. So that means for this first case, we'll be revolving about that axis, x equals to 2. So we have to figure out, this is using disk. So it told us to use disk, which we know, which would make sense. We can use disk because we can have a radius coming out from the axis of rotation, r. We have x in the opposite direction. And we know that the overall thing is equal to 2. So it's the same deal as before, where we solve for r, and r is going to equal x, it's going to equal 2 minus x. Because we know that x plus r is 2. So it means r is going to equal 2 minus x. But we need to figure out, are we going to do this in terms of x or in terms of y? That's right. No, I'm just trying to do a Dora the Explorer thing. So we're going to do this in terms of y. Because with disk, you must use the element of area or the element of thickness that is going to be perpendicular to your axis of rotation. So in this case, our strip is going to be that right there, because again, it has to be perpendicular to axis of rotation. That's dy, which means in our case, dv is going to equal pi r squared dt, and we need to get this r in terms of y, which we have x1 equal to square root of y. Or is that what this is? Okay, we have y1 equal to x, and we have x. Okay, they're just saying x1 is equal to square root of y. So, or y1 is equal to x squared. Okay, yeah. So that means that this is we'll have y1 equal to square root of y, which means r is going to equal 2 minus the square root of y. So we can plug this in for our r, pi 2 minus square root of y squared dy. Now we need to set this up for our limits. And it's going to be from y equals 1, and this will be 4. We can just plug in y equals 2 squared into this equation here to get that. It's going to equal 4. So we can do 1 to 4. Alright, so that means that we can pull out our pi here, pull out all the constants we don't need, and we can have our r squared 2 minus the square root of y squared dy. You can leave it like that if you want. It didn't say, unless they say ready to integrate. If it says ready to integrate, then you do this. You want to make sure that you can just go straight into the integral, because right now it's not ready to integrate, although it is integratable. So minus 2y, 2 square root of y, or sorry, it's 4. It should be 4. Plus y. So in this case, this is fine right here. but this is ready to integrate. You must do a little bit more algebra, and this would be considered right. So this is for ready to integrate. Can't spell it right. Or I can spell it right, but it looks like trash. All right. So we're done. That's what's in the red is just fine. These should be going pretty quickly anyways. So now we have to revolve about the x-axis using shells. Okay, so if it says using shells, what does that mean for our element of thickness, our strip? What is that going to be? A dx, or sorry, is it going to be perpendicular or is it going to be parallel to our axis of rotation? This is an axis of rotation. So it's going to be a dy. Well, it's going to be parallel. So in this case, it's going to be dy. Because remember, because we're pretty much, whenever you revolve it, you should create a cylinder, which is essentially a shell. So if I take this and you revolve it, and you get a cylinder, then you done it right. You set it up right. But there's a little bit more components you need to be careful of. So dv here is equal to 2 pi r h dt. So again, this is going to be your circumference. See, this is the height of your strip. This is the way to put it. And we know that this is the thickness of our strip. So our R is going to be from our axis of rotation out to our strip. That's R. Your height is going to be this distance here. It's going to be from what this is pretty much the length of your strip. So it's going to end up being, so this case, this is x2 equal to 2. This is x1 equal to the square root of y. So this is our height, which makes height equal to x2 minus x1. And I'll go ahead and write out what our radius is. Our radius is essentially y, because at every point, because it's distance from our x-axis. So here, this is up to y equals 1, and then every point after that, it will be varying y. So we know r is equal to y. And then dt, we've already said it's going to have to be, it's going to be dy. So now we can go ahead and plug in for all this. We can say 2 pi r being y, h being x2 minus x1, so it's going to be 2 minus x1 square root of y, dt dy. So volume, in this case, is going to be the integral, and again, it's all in terms of y still, so it's going to be integral from 1 to 4, 2 pi r, which is y, and h, which is, we said, 2 minus the square root of y times the thickness dy. All right. So now we're going to revolve this about the x-axis using washers. So this is going to be the only time where we change it up, the dx dy thing. So because remember, our axis or element of area needs to be perpendicular to our axis of rotation. And axis of rotation is x, which means our element of area needs to be a dy, or sorry, a dx. So that's our element of area. But in this case, we need to find dv where it is pi times big R squared minus little r squared dt. So big R is going to represent the radius to the very outermost edge of your disk, while the inner radius is going to be the innermost edge of the disk. Well, washer, not disk, but you know what I mean. So in this case, this represents little r here. because this is the area we're not including when we're revolving this shape around. So this represents a strip of little r. This represents a strip of big R. Right here. In this case, I'll make it equal to that height. So little r should typically be constant. Doesn't have to be, but typically. That's just easier that way. But big R will typically be varying. Usually one of them is going to be varying, one of them is going to be constant. Actually, I probably shouldn't say one or other is going to be varying or constant. But that's a typical thing. But you need to make sure that what you figure out what area you need to add and what area you need to subtract. So this is big R. That's the area we're adding for that blue strip. This is little r, so that's the area we're subtracting because it's going to be the big disk, the green disk area minus the little orange disk area to get the area from the blue washer. And then again, we always have our dt. So r in this case is going to be whatever this is, and then we have to make sure it's in terms of x, which earlier we saw that it was y1 equal to x squared. So that's our r, our big R. And then r is going to be whatever this height is, which you go back up, it's y equal to 1. So when we go and plug in for all of this, we know that our volume is going to be the integral. And we need to figure out what our limits are real quick. So go back up here to the top. We know that's going to go up to x equals 2. That's our upper limit. And I presume x equal to 1 is because we have y, so we have y3 equal to 1, and it's going to merge with y1 equal to x squared, which means x squared has to equal 1. So x has to be 1. So we're going to go from 1 to 2 for our volume. And it's going to be pi times big R squared, which is going to be x squared squared minus little r squared, which is just 1 squared, times our element thickness, which is dx. And you can leave this as 1 to 2 pi times x to the 4th minus 1 dx. All right. Big thing you just need to know: what area are you adding, what area are you subtracting, and how is that radius related, and knowing what element of area you're using for your revolution. If it's disk or washer, perpendicular. If it's a shell, parallel with your axis of rotation. Just going to reiterate that because that's just the biggest thing here. Now we have x equals 1, which is right here. I already know that point here was 1 by our last problem. This is using shell. So again, it has to be parallel. So we know it has to be dy. Sorry, we have to be, our height is going to be y in the y direction, but our thickness is going to be dx. So that's going to be our element of area. And remember, dv equals your circumference, 2 pi r, h dt. So r is going to be your distance out to your element of area. So that's r. Height is going to be the height of your strip. And dt is always going to be whatever variable you're doing it in. So we know we're going to have to do it in terms of x. And this is what tells you wherever you're revolving about and what method you're using, that's going to determine if it's x or y. So now we need to get r and h in terms of variables we need. So we know that from here to here is 1. We know from here to here is x. So we know that x is equal to 1 plus r. So r is going to have to equal x minus 1. All right, just that simple. All right, and then we need to get our height in terms of x. So it's going to be this y y1 minus y3, I think is what it is. So height is going to be, this is x squared minus 1. It's going to be the top y minus the bottom y. So now I can plug all of these in. So we have volume equal to 2 pi r. Remember, r so is x minus 1 times height, which is x squared minus 1 dt, which has to be dx. Integrating that, and we know it's going to be from 1 to 2. All right. And you don't have to simplify that anymore. You can leave it like that. It's honestly easier if you leave it like that anyways, because they're going to see that, oh, this is r. Because again, you're not setting up ready to integrate. You're just setting it up in one integral with one variable, and that's little r, that's h, dt, and they're going to recognize that. Now it says x equals 1 using washers. So same axis of rotation. R is going to be different this time because, again, it's a washer. So it has to be a perpendicular element of area. So that's our element of area. It's going to have a dy. This is going to be so then we have to do big R squared minus little r squared. So remember, what are you adding? What are you subtracting? So in this case, I'm adding this area, but I'm subtracting this area. All right. So I know that this has to be my big R. This has to be my little r. So we already got little r before. We can do the same thing we did in the last problem. Or, no, we can't. Because little r goes up to x, not the y. So ignore what I just said. But we still figure out r. So we know that this from here to here is 1. And we know from here to here is x. I mean, we can use, and we know from here, make that a little bit more clear. Here to here is x, but from here to this edge all the way out to this is 2. So we know for big R, it's just going to equal this x minus this x, so it's going to be 2 minus 1, so 1. Little r, because again, see it flips. Now big R is constant, and little r is varying. So r, little r is going to be, it's going to be x equal to 1 plus r, because again, 1 r adds up to this x, and then we can say, oh, r, little r is equal to 1 minus x. Oh, wrong way. As soon as I did that, I was like, that's wrong. X minus 1. There we go. So now I can get my so again, my dV is pi r squared minus little r squared dt, which means my volume is going to equal the integral of pi times big R squared, which is 1, minus little r squared, which is x minus 1 squared. Dt, which is again, it's dy. So now I have to get x in terms of y. So I know x and x for this one. We know that y is equal to x squared. So we know that x is equal to square root of y. So I need to flip this x for square root of y. This is all right. Then my limits are going to be, again, it's for y. So go back up to our y one. I think it's 1 to 4. Yeah, so 1 to 4 in terms of y. And I'll go ahead and rewrite this as minus square root of y. There we go. All right, big things. Just reviewing for the top. For these problems, it's going to be dv equals area dt. Figure out what your relation is for your area to whatever it happens to be. It can be a relation to x, relation to y. But note that whatever it's parallel with, whatever your direction is. So in this case, we have to use dy's because it's parallel. It's horizontal. But if it's vertical, it's going to be dx. So that's going to dictate whether you use x or y for those. For surface area, it's always going to be 2 pi r ds. R is going to be the perpendicular distance from your axis of rotation. And ds is going to be that length, or that infinitesimal length for each of your rotations. And this is a length square because it's for surface area. I know you think that, oh, I should have double the length. I should have double the surface area here because I have the outside and the inside. Just don't think about it too much. It's going to be, you just think about it for just one side and not two sides, because it has an infinitesimal thickness. So it really only has one side. So you have to use the outer side or the inner side. It doesn't make much sense, but just trust me on this. Just 2 pi r ds. So using discs or washers, your element of area is going to have to be perpendicular to your axis of rotation, and your r is always going to be parallel with your axis, with your element of area, or perpendicular to your axis of rotation. And r is always going to be perpendicular to axis of rotation. It never won't be. With shells, and we go down to shells, your height is always going to be the distance. It's always going to be the height of your element of area, and the r is going to be the perpendicular distance to your axis of rotation. Again, same deal. And that height is just going to be the top minus bottom, or right minus left, whatever you have to do to get that height. And with your dt. And again, your element of area has to be parallel with your axis of rotation. Your strip has to be parallel with the axis of rotation for shells. And then vice versa for disc and washers. Been very explicit about this. Don't you mess it up. All right, I'm going to know if you mess it up. I said it 800 times. If you mess it up, that means you didn't watch this video or you didn't listen to me, which I get. But anyways, good luck on your test. Boom, 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 good luck. And let's see what my background. It's a picture of my cat, isn't it? It's Ernie. All right. Good luck. I'm ending the video now.